Now we are ready to start tackling real-world tasks with machine learning and deep neural networks. One of those first really great tasks to tackle is recognizing handwritten digits using a neural network. And we can do this using a data set called MNIST, which has become a classic in machine learning and was actually one of the very first data sets that a neural network was trained on. So you can read about the MNIST data set. You can check out the original data and check out the Wikipedia page. If I remember correctly, it's handwritten digits that were extracted from checks back, I think, in the 70s, when it was much more common to write checks. So Flux helpfully loads this or prepackages this data for you in the flux.data submodule and called MNIST. You can use the MNIST package, just mnist.labels to extract out the labels, which are the ground truth, and mnist.images to give you the images themselves. You can take a look at these. There's 60,000 images and, of course, 60,000 corresponding labels. And you can look at just the first handful of images to get a sense of what these things are. They're grayscale, right? So there's some gray in there, black backgrounds, white foregrounds, and you can see this is 50419. You can look at what those labels are, and indeed 50419, so that's great. They're doing what we expect, and you can examine an individual image, see what its size is, right? So these are 28 by 28 pixel images, which means that they have a total of 784 pixels in them. And by default, they're just like our fruits, images of fruit back in the first lectures were matrices of colored pixels. These are just matrices of grayscale pixels. So you can see that just by looking at the type of images, and you can see that it's an array of grayscale. Actually, let's look at the type of images one. So one of these images is an array of gray something. So it's a grayscale pixel there, and it's a matrix with two dimensions. So you can see the numeric content just by calling float64 on all the elements, and that'll give you all of the numbers backing those grayscale pixels. Largely zeros around the outside. Somewhere in the middle, you'll have the non-zero white sections of the image. So those are our data, and that's what we want to try to detect. So let's set up a neural network to do this. How would we set this up? What would you do? What kind of structure, topology would you think would be appropriate here? If you recall, the previous images, we had already gotten a leg up, and they were all pre-processed for us. We had the mean red, the mean blue, the mean green amounts of the images, and that's what we used to do our machine learning task. In this case, we don't have red, green, or blue, we just have grayscale. And while we could look at the mean amount of white in each image to see what character they are, I don't think that will be very successful, right? There's a lot more information there that we can use. And in fact, we can pass each individual pixel as an input to our neural network. So let's do that. Let's first make sure that all of our images are the same length, and indeed they are. They're all 784 pixels. And indeed we have 10 unique labels, right? 0 through 9. So if we're going to use each pixel as its own input, that means that we'll have 784 inputs to our neural network. So it's going to be our n inputs, and we'll have 10 outputs. So you can start getting a sense of what our topology of this network is going to look like. First, though, let's create the features that will pass to this neural network. If we're using each pixel as a independent feature, we need to create a vector. Right now, they're in matrices of grayscale pixels, right? And we want them to be as vectors of floating point numbers. So we can create a pre-processing function that will just take the float64 of every pixel in the image to convert them to floating point numbers, and then use the vec function to convert the matrix into a vector. So let's pre-process the first 5,000 images in the 60,000 image data set. Why only 5,000? Well, let's keep our training times low. So if we only train on a small section of the data, it'll be faster to train. The other reason is this way we also have a good amount of data held out that we can use as testing data and holdout data to make sure that we're not overfitting our model to the trained data, and to make sure that when our model sees novel data, it'll perform appropriately. So by holding data out, we can kind of simulate what the performance of our model will be with novel data. For labels, we can use one-hot to create them, right? We're doing a categorization task. We're categorizing, is it a 0, is it a 1, is it a 2? And while those are numeric numbers, we're not really fitting them to numeric values, right? There's more meaning and structure to them than just them being 0, 1, 2. So we don't want one output, we want 10 outputs. And of course, we'll use one-hots to represent, the probability that a certain answer is a 1 or a 2 or a 3 or so on for each element. And again, we'll just use the first 5,000 elements. Now, we're going to be doing this a lot, so instead of manually doing this and piecing this together, let's create a function that'll create a batch for us of a given range of images in our data set. So let's pre-process all our images. This should actually just call the pre-process function. All of our images in images of R. So that creates our x's. Our y's will be based on our one-hots, and we'll return the batched matrices of our feature vectors and our label vectors. So that way we can do this efficiently and quickly. So that creates our batch. And let's create a training batch. So this training batch will be a batch of the first 5,000 images. So now we have our data set up. We're ready to go, and all we need is a machine learning model to work with. So let's set up our neural network. We know how many inputs we have. We know how many outputs we have. Let's start just with a one-layer neural network, right? We learned in the last class how to do multi-layers, but let's start and see how well we do with just one layer as kind of our ground truth. So that's going to be this dense network with our 784 inputs, 10 outputs, and we'll use the identity function as our nonlinearity, right? Because we're passing it then to the softmax normalization to get a probability. So that will give the softmax the whole dynamic range and allow our model to express those values. And again, we'll use the cross entropy loss function as that's appropriate for comparing probability distributions. We'll just use the plain old SGD again and pass the parameters of our model to it so that way it knows how to optimize them. And we'll train it on our training batch. And you can see it takes some time, but it's pretty quick, so that's not bad. Just as before, though, we'll want to run this lots of times in order to work on getting a convergence. So we can use the iterators.repeated function to create a repeated iterator that will, continuously yield our training batch to Flux. It doesn't copy the data, it doesn't waste space, it's just a lazy iterator, which is very helpful. And so we can see what our current loss value is after training just those handful of times above. And we can, again, train just one more time and see if our loss value is decreased, and indeed it has. So we can keep track of our loss value of our training data set as we go through. And that can kind of be a nice way of keeping track of how well we're doing. And it gives us a little bit of insight into how the model is training. Of course, we don't want to just keep going back and forth, like training one step, testing the loss, training another step, testing the loss. So Flux provides what are called callbacks. Now, callback is simply a function that we can create and give to Flux, and Flux will call for us at appropriate times. So an example of a good callback here is just to show what the loss of our training batch was. And then if we call Flux, say with a 3 repeated iterator of our training batch, with this callback passed to it, it's an optional argument, it's a keyword argument with CB as the keyword, short for callback, and you pass it to it. And so after each step, it will print out the loss. And you can see we continue improving on our loss value here and every time. But now, really, we'll want to do this hundreds or even thousands of times, right? And so I don't want to have thousands of outputs coming through my Jupyter notebook to every time I train my model. And it's expensive to compute the loss over our entire data set, right? It takes some time to do. It's a computation that's not trivial. So Flux provides a nice throttle function. That's just kind of a handy helper function. And what that does is it holds on to your callback. So you give throttle your callback, and you also give it how many seconds to wait between calling your callback. So it kind of gives a delay between calling that callback that you pass. So we pass it just like what we did before. So it's in the CB, but we wrap it with this throttle argument, and we'll call it every second, say. So now we can train our training batch 40 times, and every second it will output the loss value. It took us just about 2 seconds to do this, so it only printed twice, but each time it printed is representative of about 20 iterations. Excuse me. Now, this is just the loss of the data that it's training on, right? We're also interested in the loss of data that's novel to it, new data, and we can create a test data set, a batch of our test data using that create batch function of the next 5,000 elements in our data set. And with this test batch now, we can examine both the train loss and the test loss simultaneously as we walk through our data set. So this is another callback function that I'm defining here that just updates our loss for the, stores the loss values in these vectors. So that way, each time it gets a callback, it'll add the current loss value to those vectors. So that way we can introspect them, see how we're doing, and plot the loss values over time as we've done it. So that will do it. It'll also print out the current values so we have something to look at while we're training. So let's train this 1,000 times and pass the update loss function as our callback. So this is training repeated iterators 1,000 times with that callback as our as an optional argument. So let's run this, and now every second we're going to get an updated loss value. First thing to notice here is that indeed our loss values are decreasing, and quite rapidly, right? We're already down from, I think we started at 2 at the beginning, back when our model wasn't trained at all. And we keep improving, going down towards 0. The other thing to notice is that our loss of our test batch is greater than the training loss. And this is what you would expect. The test dataset has numbers that the model has never seen before. In fact, it could have very strange model numbers that aren't well written, and the model has no hope of detecting those or predicting those because it's never seen anything like it before. So that's what we would expect. And if you see a test loss that is less than your train loss, often something is wrong. So that's something to look out for and check on, because you may have messed up some indexing or something along those lines, and some of your test data is actually in your train data without you realizing it. So you can see we continued converging, or got a little slower as we went, and we can plot these to see how we did. And this is a very typical graph that you may see. So the loss value is on the y-axis, and the approximate number of seconds of training that we went through is on the x-axis here. And as we went, we're kind of asymptoting towards not 0, but some non-zero value. And the training data set also is decreasing, but slower, and there's a gap between these two. So there's some techniques that you can use to decrease these gaps. I'm not going to discuss those today, but keep that in mind that there are ways of doing that. But this is a great way of introspecting how your model is doing as it gets trained. Now let's test our model, right? We already know a little bit about our test loss, but the loss isn't really what we're after. Really what we're after is the accuracy, right? And the accuracy is given by which of our images is most likely to happen. So let's look at this 5001st image. It's a 7, a little bit of a sloppy 7, but I think that's a 7. And indeed, the label says that it's a 7. So we're outputting now the labels and then the model's output. So we're evaluating the model at that preprocessed image and then finding the maximum value thereof. So with 70% certainty, you could say, the model is saying that the output is indeed a 7, which is great. And you can look a little bit deeper at this. You can see the entire 10-element vector output of our model. Again, we need to pre-process our images just like we did for training, and we need to do this in exactly the same way that we did for training. So that's why it's important to have a function there to do that. So now you can see, and if you look, where is the highest value number? It's here, which is 987, counting backwards. It's interesting to look at what other numbers there are, right? A lot of these are very tiny, so don't be alarmed by the 5 points and the 6 points. Those are actually times 10 to the negative 5, so those are very small numbers. But if you look, 0, 1, 2, 2 is the second most likely number that this is. And you can kind of imagine how this is kind of like a 2 that's just missing a bit of its loop there, which is interesting and kind of cool to see. It's always interesting to see how things mess up. Let's keep going and look at a few more of these. That's a 3, which we get with high confidence. The 5003rd element here. Now, this is a 4, but it's kind of a sloppy 4. So the label is 4, but we're saying with 67% confidence that we're getting a 9. So that's a place where we're missing, right? And let's look at what the total output here is. So here is our 4th digit right here at a 0.23, and here's our 9th digit at 0.67. So that's what the model is seeing with this. So let's summarize these values, right? We want to see what the prediction was, so we can ask what the prediction is for our model, given the preprocessed. And then let's look at how many of our images in our test data set, so from 1 to 5,000, does the prediction match the label? And you can see a total of 4,600 some match. We can divide by 5,000 to see what percentage we have, and it's about 93% accuracy. If we look at our test data set from the next 5,000 images, we're only 4,400 or 4,500 images are there. So normalizing that by 5,000, we get about 90%. So this is our training accuracy and our testing accuracy with this model. Not great, but it's passable, perhaps. It depends on your own restrictions and needs as to how good this needs to be. But we can start thinking about ways to improve this prediction, right? You already know how to do a deep neural network. Maybe that would make things better. Maybe there are other techniques we could use to do this. And one of the great things with Flux is it's very easy to try these things out and play around with them. So I encourage you to do that. And in fact, I'm going to do that right now with this. So let's look at how this was. So before our model looked something like this, right? Where we had a chain from our 784 inputs directly to our 10 outputs, normalized with a softmax function. Let's add a hidden layer. So let's say maybe 20 hidden neurons. So we'll have 20 hidden outputs, and those 20 hidden outputs go to the 20 inputs of the next layer. We'll use the ReLU function as our activation function. Now, what's the ReLU function? Before, we've been using sigmoids or identities. You can just look at what the plot for that looks like. Plot the ReLU from, let's say, the -5 to 5. And you can see here, it's just a simple step function going, it's 0 if it's negative, and it's a identity function if it's positive. So that's helpful. And it's a simple nonlinearity that you can try out and see if that improves things. So let's use the regular function, and again, we'll normalize with the softmax. We'll keep our loss function the same, but let's change this was an SGD, stochastic gradient descent algorithm. Let's change that to an atom optimizer. And there are lots of different optimizers, lots of different things. You can ask Flux for help on the atom optimizer, and it gives you lots of different parameters, and it simply points to the archive paper that defines this. It's an extension of stochastic gradient descent that tends to do a little bit better. So let's use that. So let's define this model. Let's reset our train loss and test loss vectors, so that way we can pass this callback that's throttling to update these values every second, and simply train 1,000 times and see how this does. So by adding this extra layer, we're adding lots of extra parameters to our model. So hopefully our model will be able to incorporate model the data much better. And you can see here we're rapidly converging. Our training losses, wow, that's going way faster and way lower than what we had seen before. So this is really cool. And you can see that we're getting down to a training loss of 0.04. I forget what our training loss ended up with earlier. I believe it was somewhere around 0.19 maybe, or 0.3 or so. Definitely not anywhere close to 0.34. But something else kind of funny is happening here. Look at what's happening with our test loss. So our test loss also rapidly decreases to about 0.3, but then at some point here it starts getting worse. And you can see that we're not doing any better. We're not asymptoting towards 0. So what's happening there? Well, let's plot and see what's going on. And you can see that the training loss is definitely improving. It's actually getting towards 0, which is exciting. But it's happening at the cost of our test loss, right? Our test is getting worse as we get better. So what's happening? Well, think about what we've just done. We added a lot of parameters, like a lot of parameters. We have 784 inputs times 20 neurons plus the 20 biases. So we have a 784 by 20 matrix, right? That's the weights plus 20 biases. Plus, those 20 inputs then become the inputs of a new neural network layer, and those become a 10 by 20 matrix of weights for the outputs, plus 10 biases. So all told, we have 15,000 parameters in this model, which is a lot of parameters. Before, we had 784 times 10 plus 10. So we had 7,000 parameters that we could tune with our data and train with our data. So you can see that we have lots of liberty to train our model, and what's that doing is it means that we end up overtraining with our limited amount of data. So there are ways you can tackle this. You can use more data. So instead of the first 5,000 elements, you could try to use the first 30,000 elements or so, see if that improves things. You could also realize, maybe this hidden layer is too big and we need a smaller hidden layer, or we need to do other things. And I just want to give a little bit of a teaser of what those kinds of other things might be. So remember, we're looking at images. That's where we're starting. And what we're doing is we're pre-processing these images in kind of a funny way, right? We're pre-processing these images to end up with these vectors. And they're just vectors of floating point numbers. And each one of these numbers is an independent input to our model. And in fact, these numbers don't know which numbers are around them. There's nothing in our model that says, hey, this 0.67 is right next to a 0.99, and that might be important. Each one of these is treated completely independently, and it's just kind of gibberish, right? If we look at this, I wouldn't be able to see that there was a 7 tucked away in here. The numbers aren't in any sort of structure, and definitely not the structure that we have this 5 here. So you might want to start thinking about ways in which we could structure our neural network topology that preserves a little bit of the information about which pixels are near each other. So, for example, when we look at these, we see the connected regions, and we see, you know, these pixels are near each other, and they're forming the leg of this 5, and these pixels are near each other, and they're forming the hat of the 5, and so on. And so, what the computer is seeing right now, the way we have our neural network set up, is just each pixel independently removed from everything else. In fact, we could shuffle these images. We could take these images and completely reorganize them in a way that, you know, if we just have a permutation, so we can create a rand perm 1 to 28. So those are our, whoops, need to say using random. Oh man. Right, 28 digits. So it's a rand perm of 28. So these are a random rearrangement of our images, right? We could have just as easily displayed our images as images of 1. So this is our 5. We could rearrange them like this in some random permutation. And as long as we keep this structure the same, the neural network would be just as easily, and in fact, just exactly the same, detect the number 5 in this raw data as it does in the data that we're giving it. So we want to preserve some of that structure, and the way you can do that is, you know, we've been using these dense neurons, and they're called dense because they have connections from all the inputs to all the outputs. Well, maybe that's not what we want to do. Maybe we should just have some of the inputs connected to some of the outputs. And that's what a convolutional layer does. And Flux has a convolutional layer built in. And this is a very, very frequent neural network technique, especially with images, where you want to be looking at subsections of the image to preserve that structural information. So that way, certain parts of the neural network just see, you know, the bottom left-hand corner of the image, and others see the bottom right, and so on and so forth. So that's a convolutional layer. Lots more to talk about there, but that's for another time. For now, I just want to finish up and say that, you know, we're using exactly the same kinds of structures that you've seen all throughout, and we're doing a real task, looking at real evaluations, and able to predict handwritten digits. So thanks for joining us, and hope to see you around. Bye-bye.